So quick show of hands. How many of you have written some Clojure, read a book, written a few lines? How many of you have written code in another Lisp, common Lisp scheme, Racket? Okay, so that's most of you. So I'm going to just go very quickly over all the introductory material that I prepared in sort of the worst case scenario. Lisp is made up of S expressions. They're delimited by parentheses. The first term is always the function. The remainder of the terms are the arguments of that function. These are some S expressions. Here we see the addition of 1, 2, and 3 using the plus sign, which is always a prefix notation. We can also create a list of 1, 2, and 3 by calling the list function. We can quote that and get a similar effect. We can also quote the addition. In this case, the plus sign is a symbol, not the actual addition operator. In order to figure out what that means, we need to resolve it, which is what eval does when we evaluate that quoted form. Lisp is a homoiconic language, or a family of homoiconic languages. The Wikipedia definition here could be taken in a very literal sense to apply to any language which has a primitive string representation. And so the key thing here is to think about not what the source code is for you, but what the compiler sees the source code as, right? And so we're talking about not the source representation, but the AST representation. Macros are a compile-time AST transformation. And so the key thing here is that this happens after reading, but before the code is actually emitted. And it is scoped. It is not a pervasive transform of all the code. It is something that occurs within a given scope of your program. A very simple example, a common sort of introductory example, is the unless macro, which is the complement of the if form. Here we take a predicate and a body, and we generate a list that represents an if statement where we have the predicate and we move the body into the else clause. So these two expressions here are equivalent. And this seems a little bit trivial, but it's important to realize that this has conditional execution of the body, which would not be true if we had an unless function, right? We'd have to pass in the body, have this side effect if we had just a function here. And so this is a crucial thing to have if you're in an eager language. If we're in Haskell, it's a completely different story, but it's sort of out of scope. So Paul Graham, back in his sort of patron saint of Lisp days, talked a lot about Lisp and talked a lot about macros as sort of the thing that made Lisp a language worth using, right? He talked about it as this thing that if you were in a sort of lesser language, you might not even realize that you wanted it. But once you sort of wrap your head around it, you couldn't imagine life without a macro. Conversely, I know a number of people who have been using Clojure in production to good effect for a number of years, and they have effectively disallowed the creation of new macros in their code base. There are existing macros in Clojure, you can use them, but you better have a damn good reason for adding a new one. And I think that this is a crucial disagreement. Because whatever you think about Paul Graham in his sort of latter-day investor sort of persona, his qualifications, the qualifications of my unnamed acquaintances are pretty much the same. They've used Lisp commercially to good effect. And so this talk is not about macros in terms of what they can do, or macros in terms of how we can sort of theoretically make a better way to define code forms or something like this. This is a very sort of practical, pedestrian exploration of what macros have been used for. And the way that we're going to look at that is looking at macros which are written in Clojure, which is a particular dialect of Lisp, which is sort of concerned with the dual sort of goals of being immutable by default and having seamless interop with Java, which is not immutable by default. And most of these macros are ones that I've written because when we're talking about macros, it's not, again, a question of what is possible, because anything's possible. We can make any piece of code mean anything that we want to. The question is sort of what is in good taste. And that is very sort of mired in the problem that we were trying to solve, and I can speak most authoritatively on the problems that I was trying to solve. So the first Clojure project I ever wrote was an OpenGL library. It was a library called Penumbra. I was very pleased with it until it got kind of large and out of control. It was a layer over a Java library called, oh, yes?
Maybe I can ask a question. So you say we can make any program mean what we want it to mean, but can you overwrite existing meanings?
I mean, so what we're getting, I mean, so let's say if is a special form in Clojure. If within the scope of our macro we see an if symbol, we can transform that to mean something else, right? These are, the code is coming in as something without semantics. It's just these sort of symbols, and we can go and make every if mean the complement of if we want to. It's not.
So you could really say at the start of the program you open your macro, and at the end you close it, and then inside you do whatever you like.
You do whatever you please,
Okay.
and so we're not sort of controlled by what we can do. It's by what we should do, or what is sort of reasonable to do.
Okay, good.
So the library that I wrote was a layer over LWJGL, which is a Java library that has FFI bindings to the C library, which is a spec by the Kronos Committee, which is a collection of game developers and hardware vendors. And when we have these sorts of towers of abstractions, all of which are trying to be helpful, right? All trying to be idiomatic in their own particular language, we have this sort of veering effect away from the sort of essence of what we're trying to do, right? They try to present it in a way which is nice for them, but it's less nice for whoever's trying to sort of build atop them. And so I, as a Clojure developer, am sort of building on top of this leaning tower. And so when you look at OpenGL as it's done in C and pretty much actually quite literally Java, you might do something that looks like this, where you enable the lighting, and then you call push matrix, which is a way of defining a scope for spatial transformations, right? When everything that is within this pushed matrix will transform to the moment that we pop the matrix back off, we return to our original state. And so then we translate along the z-axis by -10 units, and then we begin to draw a series of quads, or in this case, just one rectangular shape. And then we end our draw, and then we pop our matrix back off. And it's worth noting that there's a lot of balancing here, manual balancing of calls. And we've indented the code because that helps us sort of reason about it. But that's only because C and Java don't give us any better way to deal with this, right? We hope that we won't have an unbalanced call because what will happen will be inexplicable. And so, you know, if you had a language construct like Python's width, this would be sort of something that you could solve. But neither C nor Java have it, and neither does Clojure, but the nice thing is that we can just sort of make one for ourselves. And so equivalent code in Clojure looks like this, which does exactly the same thing, but notice that both in the case of the push matrix and the draw call, we don't need to close this off. That is implicitly sort of described by the scope, right? Because we've defined some macros. And so the push matrix macro is pretty simple. We just want to take whatever the body is, whatever these sort of series of calls are, and push them inside this sort of initial call and the closing call. And you know, here we push the matrix, and then we, within a try finally clause, run the body, because the body, you know, for some reason throws an exception. We want to make sure that we, as that sort of exception pushes up the stack, clean up after ourselves, right? Make sure that we're always in a balanced state. And so if we use the same mechanism that we used for the unless macro, we get something like this, which works, right? But sort of only kind of resembles the code form that we're trying to do here. We're trying to do a bunch of things. We have a manual list. We have some quoted forms. Since the body has multiple arguments, we have to concatenate everything together. And this is far from ideal because we're trying to represent code, and it's very easy to have nesting one level too deep or one level too shallow, and then the code might work, it might not, and it's going to be very hard to sort of visually debug this. And so it's in our interest to have our definition of the sort of templated code that we want resemble the code that's generating as closely as possible. And so in pretty much every list under the sun, there's something called a quasi-quote or syntax quote. And it's, again, just a form of sort of code templating. And here we see that where we have the sort of ellipses body, we've replaced that with a tilde at symbol, which is basically splicing in the code and then saying I want to splat it out. And so this is very simple, right? This is a big win because what we've done is we've taken something that was sort of incidental busy work for the programmer. We've made the compiler just do it for us, right? And we've created this linguistic extension which makes no sense outside of the scope of drawing things for the OpenGL API specifically. But that's okay, right? It's not something that anyone else will ever have to use. A more sort of thorny issue is how we go and actually create closure equivalents for all of the existing Java functions. We have a GL push matrix function that's exposed by the Java API. We want that to be GL dash push dash matrix because we like our kebab case rather than the camel case. And one sort of quirk of the Java library is that it wraps all of its objects in this one big class that is tied to whatever version of the OpenGL spec it's from. And so you have a GL11 object, a GL12 object, a GL20 object, and on and on. And this is sort of useful from a bookkeeping perspective, but it's not interesting to me, right? I just want to kind of get at the functions that I have. And there's not duplicate sort of definitions of these two functions. And so from my perspective, sort of having to specify which object this is contained in is needless effort, right? It's an answer that the computer can give to me, so there's no need for me to specify it. And so we can imagine a version of this which is lacks that, right? It just via reflection goes and kind of scans over all the possible containers and finds it for me. But if we go that far, we can imagine going one big step further, right? Having a batch import thing, something that just goes scans over the object or all the objects and just sort of imports them all one by one. And this is not something that I did. And the reason for this is debatable, but basically we want to consider our audience, the people who are reading the code, right? Because inevitably they will call a function incorrectly, they will get an exception, their stack trace will take them to this thing, this GL import all, whose behavior is not defined by the code, it's defined by some weird nexus of my code, the sort of implementation for the underlying Java library, which is tied to the underlying spec in C. And so this poor person using my library, now in order to understand any one part of my code, has to understand the entire OpenGL spec, which is unkind, I think. And so when we think about this, when we look at macros, right, this thing with which we can do anything, one of the key distinctions that we want to make is between sort of compression in the information theoretic way, right, gulfing our code down to the least possible number of terms, and concision, which is to say going down to the essence of what we're doing, but not taking away anything further than that. And the sort of controlling force of where on that spectrum we fall is our audience, who needs to be able to read our code. And our audience includes us now, us 3 months from now, when we've kind of no longer think that we are quite as clever as we were, and anyone else who might read it, right? Which is an audience that you may or may not be able to completely predict, right? You may know that this is some sort of deep implementation detail, and you can get away with a lot more compression, a lot more cleverness than you might otherwise. Another sort of example of this trade-off is a library I recently wrote called Manifold, which has a deferred type, also known as a promise or a future. These are sort of a dime a dozen in all the other languages. And one of the sort of frustrating aspects of this construct is that if it gets into an exception state, but that's never consumed, it's never sort of grounded out, it just vanishes, right? Eventually the GC gets it and you never know that anything failed. And so if I went and I posted something to a server and never actually paid attention to what the response was, that might have just failed. It might have done something wrong, but I assumed happily that everything sort of went as expected because nothing was logged. And so one way to kind of address this within the JVM ecosystem is to define a finalize method, which just before the garbage collector does its thing, examines it, sees whether it's in an error state, sees whether anyone has ever actually paid attention to the fact that it's an error state, and if not, it logs the error. And this doesn't have any sort of temporal coherency, right? An error occurs, a bunch of time passes, GC happens, and all of a sudden, boom, there's an error in the log. But at least it's something, right? It's some sort of evidence that something went wrong. And this was a great idea up until the point where I realized that having a finalize method adds a tremendous amount of overhead to GC. I'm not entirely clear on this. Just the presence of an empty finalize method adds a lot of overhead. And I think they go into different queues or something, I'm not sure. But it was clear that I could not get away with this. And so what I needed to do was to create two different objects that very closely resemble each other, but for this one finalize method. And I have an error logging deferred, which one time in n, in my case every 1,000 instantiations, will create this unduly expensive version of the deferred. And this means that there are a lot of errors that are obviously going to go missing, but if we're operating at scale, and this is sort of a pervasive error, there will be evidence, right? There will not be a complete sort of swallowing up of this error. But of course, now I'm in the business of having to duplicate all the other code here. And this is because def type, its API is syntactic, right? I can't pass it a map. I can't give one a map that has the finalize method and one a map that doesn't have the finalize method. I can't do anything at sort of a data level to address this. I have to give both of them this sort of expanded out syntactic representation of this class. And so I use a macro. And I want something that looks kind of like this. I have a both macro that wraps this. And at various places within this, I have some either clauses, right? Which says first what I want in the one class and then what I want in the other class. And so at the top here, I have deferred and error logging deferred. And I have nothing, and then I have the finalize method. And this is a very big win for me because the both macro, and I'm not going to go into the implementation very deeply, but it's very simple, right? It's about 10 lines of code. It has something that scans over the top level of the form and looks for these eithers, and first expands out with the first term and then expands out with the second term. And so I've gone and used 10 lines of code to save myself hundreds of lines of code. And hundreds of lines of code that need to be kept sort of manually in line with each other, right? You could get these drifts where I make a change in one but not the other, and that would be almost invisible to me. That would be impossible to track down until someone reports some sort of weird quirk. And worse yet, a weird quirk that only happens one time in 1,000. But this is good in a way that the sort of batch import case was not good, in that it sort of respects the code that was handed to it, right? It is a transparent, for the most part, macro. We have these little sort of quirks, these little either clauses, but unless someone is looking at particularly the finalize method, they might not even notice that this is a thing. They might not notice that there is this little bit of cleverness there. And if it is something that they notice, they can go and look at the macro, and it's reasonably apparent what it is that it's doing. And so this is more respectful to our audience, right? The proportion of our audience that is ever going to even come across this is much smaller than it was when we were defining every single function via this sort of opaque macro. So macros are useful, right? They give us these sorts of degrees of freedom that we wouldn't otherwise have. And so it's worth asking, like, why are all these people avoiding them? Why is the Clojure community sort of gun shy? And I think that one answer is that, as I've articulated, there's a balance here, right? There's sort of balance between trying to reduce the amount of code that you're writing and still having it be something which is legible. And that's a difficult line to walk. It's something that I've failed to walk correctly a number of times. But there's actually something a little bit deeper at work here. And to look at that, I'm going to return back to graphics. In this case, the Sierpinski triangle, which is a sort of simple fractal shape. And it's generated by taking a triangle and shrinking it by half, and then doubling it, or rather tripling it, then shrinking that by half, and then copying it twice again. And on, right? And we look at this and we see that there's sort of this nested regularity, and we realize that we can use macros. We can define a Sierpinski macro, right? That takes somebody, we don't really know what it is, we don't care. We put it in a function, and we then define a sort of local context in which we can do transforms, and we shrink everything that we draw within this context by half. And then we render it 3 times, first in the bottom left, then the bottom right, and then above. And we can nest Sierpinski macros to our heart's content. We can do it twice, we can do it 10 times, but at some point this gets sort of tedious. And so we decide that we want to stop having to type this over and over again. And so we define another macro, which allows us to just give a number of Sierpinskis, and it goes and wraps it for us because, the computer is better at that than we are. And this works. We can go and we can, do 5 levels deep, we can do 15 levels deep. At some point, the code that's being expanded here will make the JVM a little bit cranky, but it's because we are not copying the code 3 times, we're just copying it once into this function, it's sort of a linear relationship. It's not too bad, right? We can actually get away with this a lot longer than you would expect. But there are some definite problems here, one of which is that this is imperative code, right? We're drawing something and then we're done. And Clojure purports to be a functional language, and this is not really in line with that, right? We have no ability to use all of the tools that sort of Clojure can bring to bear. And the other problem is that, as we saw, when we wanted to have sort of a higher order of abstraction over this macro that we defined, we had to define another macro, right? Because the API is the syntax. We have to provide the syntax in the way that it sort of expects it. And so macros beget other macros. It's kind of unavoidable. So maybe we should use functions, right? Maybe that's better. And we can do this actually very simply. We can just simply call our draw triangle function something else. We can call it a renderer. And we can choose not to immediately render it. We have a function called render which invokes it. And based upon this, we can begin to create these sort of higher order functions, like this one, which goes and takes a function and returns a function which renders it somewhere else, right? And using this and other sort of similar tools, we can define a Sierpinski function, which takes a function and shrinks it and renders it 3 times. And then we can do something that is much more closely resembling sort of functional programming. We can define an infinite lazy sequence of all the Sierpinski shapes. And we can choose one of them and we can render it. And this is significantly better. It's a small change, but it's a very meaningful one because Clojure is, at its heart, a data-oriented language. It takes data, it transforms data. And functions are not a very rich form of data, but they are something, right? There is a separation between describing what we want to have happen and actually having it happen. And that's a really important sort of separation, right? That actually enables a whole host of things that you wouldn't expect sort of intuitively, even as someone who is an experienced Clojure programmer. So why do we avoid macros, right? Why is there this hesitation? There's this sort of truism when people talk about Lisps that say code is data and data is code. And the first of these is certainly true. But code is a very small subset, a very narrow subset of data. There's a lot of data that is not valid code, an even smaller amount that is syntactically, or rather semantically valid. And macros, as their API, require syntax, right? Which is, again, this narrow subset, this thing which is harder for us to generate. Hence, all these sorts of affordances, these syntax, quote, sort of templating mechanisms. And because macros sort of beget these other macros, this has this tendency to sort of infect the surrounding code. It makes it kind of fragile. It makes it sort of calcified. And so the reason that people avoid macros is because they've been bitten by this one time too many, right? They have gotten sort of shy of driving off the cliff after they did it the first 5 times. But there are some really good reasons to use macros, which are closely related to the reasons not to. Macros use syntax, not data. And syntax has the enormous benefit of having well understood semantics, right? Data doesn't have semantics. Data is data. We have to describe what the semantics are. We have to document it in exhaustive detail. We can write something that is not quite Clojure but closely resembles it, and people will understand intuitively how it is meant to be used. That is invaluable. It is also the only way we have to create control flow abstractions, right? It's the only way that we can have conditional execution of code. This is not strictly true. We can go and wrap everything in functions, but in practice, you don't really want to do that. And we can solve problems at compile time that otherwise we would have to solve at runtime repeatedly. And when we're able to do that, we should always try to. So one fairly well-known version or use of macros is the CORE.ASYNC library, which takes most of the things that Go has for concurrency and steals them and puts them in a library without any sort of changes to the core compiler. It has channels and it has this macro called Go, which will walk all the code and sort of allow it to be used in a lightweight thread context. And it does this by examining the code for all the places where it might have to pause, which in this case are when it's reading in a message from the in channel, and the in channel might be empty, or it's writing out a message to the out channel, and the out channel might be full. And in each of these cases, it may need to pause, might need to wait for that sort of condition to change. And in order to sort of allow for this, it takes this one function, this one code form, and sort of rips it apart at the seams, turns it, in this case, into 3 different functions, which are linked together as a sort of finite state machine. And this allows for multiple sort of Go routines to be swapped in on the same thread. Whenever a particular Go routine is parked, waiting for something to happen, it will go and just sort of cede control to something else. And CORE.ASYNC, and more specifically the Go macro, is a really impressive piece of engineering, right? It is an enormous example of the power of macros. It's something that anyone could write in practice. It was the people who created CLOJURE that wrote it, but anyone could have written it. And it works both in JVM and JavaScript, which allows for both of those environments to have a shared concurrency model, which is actually tremendous and sort of unprecedented. And it has the identical flow of execution to the existing sort of Java model, right? Which is when I cannot proceed, I will just stop and wait. And again, this sort of falls into the need for macros to resemble the things that they're emulating, right? We can't just sort of needlessly go away from what people expect. At the same time, there are some problems, right? The Go macro is a very impressive piece of engineering. It took about 1.5 years for it to get right. It is about 1,000 lines of code plus about 2,000 lines of syntax analysis that got sort of factored out into another library. There are some issues. Even though it tries to sort of transform everything, all possible code forms, it cannot transform within a closure because that function may escape that scope and they can't control how it's being executed. And there is another problem here, which is that it does actually very closely resemble the Java thing. It has this sort of sequential flow of execution. Anytime any piece of data is not available, it will just park itself and wait. And when we consider how most backend servers work, most backend servers are a front end to other backend servers, right? A database, any other sort of service. You have microservices galore. And so we might have a request come in, and that gets sort of farmed out to a bunch of other backends. And then we take the responses from the A and B services and feed those into requests to the D service. Then finally, when all of those are done, we feed the responses from D and C into some function that gives our response, right? This is far from an unfamiliar situation. And if we have this sort of sequential flow, we have to be very careful about separating when we send a request and then when we wait on its response, right? We have to wait or sort of dereference these responses in a very particular order. And if we fail to do this, our program will not be wrong. It will not respond with an incorrect result. It will just be needlessly slow. And this is a very difficult thing to debug. We often have no tools that will give us like a Gantt chart or something like that, akin to what you see in a JavaScript console, that will sort of show us when we have this suboptimal sort of behavior. And so that's not necessarily something which is our fault, because the computer knows what the data flow dependency is, right? The code is an unambiguous representation of what relies on what. And if we imagine a macro that is not trying to do the whole CORE.ASYNC, not going sort of full CORE.ASYNC, but is just trying to look at a particular let binding and understand what the relative dependencies between all the different terms are, we can do this, right? We can take this and kind of look at what the different dependencies are. And because we don't want to spend 1.5 years trying to get this right, we might try to do something a little bit simpler. And as a sort of naive first approach, we can imagine just looking inside these terms, right? We look inside the sort of definition of D to see what D relies on. And we can see that there are both A and B symbols in there. And we see that there's some A and B symbols in our let binding and success, right? Except if we have something a little bit more complicated, we kind of get led astray, because here we have an A symbol, right? And we see this A symbol again, but this is not the same A symbol, right? The fact that they're simply the same thing, have the same name, doesn't mean that they are the same value. And so one problem is that these two A's are not the same, because this A below it has been shadowed, right? We have a new lexical binding, a new lexical scope that's being defined. The other one is a little bit more subtle, right? We don't have a new lexical scope here. It's just that the A above and the A below are not actually expressions. They're not references to some sort of computation that's going on, right? This is just a lexical definition. And when we're trying to scan for what is being used, what is being computed on, that is not the same as what are all the symbols in my code, right? The expressions are a subset of the S expressions in our sort of code from a runtime perspective. And so what we need is a way of understanding our lexical context, right? We don't really want to have to compute it, but if we have to, then we will. And we need a way of avoiding these sorts of non-expressions if we're just trying to understand what is being computed, right? And so I actually ended up writing a library to do this because there wasn't a particularly good way to accomplish this. And one of them is a thing that simply walks over all the expressions, right? Very straightforward. And then there's another thing which is a little bit more subtle, which is as we were walking the expressions, we are feeding this code into the Clojure compiler, into a sort of sandboxed instance of it. And at any point while we're walking, we can ask, what is my lexical scope? What are the terms that I have access to? And because Clojure allows you to apply metadata to symbols, when we define our sort of outermost scope, we can apply a metadata that says, I'm the A that you care about. And then when we go and see an A and we match it up, we say, is this an A that I care about? And within this sort of shadowed context, the answer is no. And so this is not hard. This doesn't actually require any sort of deep understanding of the compiler or even the language, right? This is just the visitor pattern, if you're into that sort of thing. And that is powerful, right? It means that we're able to sort of differentiate between this by simply examining the code in a particular way, right? And so letFlow is not in any way an attempt to compete with what the Go macro does. It is a sort of different way of just kind of addressing this problem, but it's very small. It's only about 40 lines of code. And there's about 200 lines of code in the sort of code walking library that it leverages. And it's able to do this not because it's better, but because it just leans very, very heavily on the existing implementation of the compiler, right? It does not need to take a pyramid and then build an identical pyramid next to it with one stone askew, right? It can just take that existing pyramid and sort of add something. Another sort of slightly ridiculous thing that you can do in this vein was a library that I wrote kind of just to play around with this idea. Yes? Oh, 5 minutes. Okay. Was a library called Proteus, which just defines a let mutable macro, because Clojure, of course, is an immutable language. You cannot overwrite a value which has been let bound. But now you can. And so all it does is it allows you to use the setBang method inside of its scope to overwrite a particular value. And how it does this is not particularly complicated. It just expands to something like this. It takes whatever the value is, it wraps it in a container object. It looks for every instance of this x, and it does a get wherever it is. Whenever you have a setBang, it does a set. But this actually has a nice property, which is because this value is constrained to this lexical scope, it's safe, right? This is not unsafe mutability. There is no race condition that can occur. Only one thread will ever see this. And because it has this lexical guarantee, it needs to be no runtime checking, no nothing. And so this actually ends up being faster than any other state container that Clojure provides, because Clojure makes much more pessimistic assumptions about who can see this particular value. The only sort of wrinkle here is that if we try to close over the value, then it can escape, and it is unsafe. And so we have to make sure that what's being closed over is not the container, but the value at the time that it got closed over. And so this is, again, very simple. It's about 100 lines of code. It's kind of a joke, but people use it. And this and the sort of letFlow and any of the other things that I've sort of talked about here are not meant to be sort of the apex of what's possible. As I said, I'm actually trying to go for fairly pedestrian examples here that are not going to necessarily inspire you and go, yes, macros, they're amazing. These are experiments. But I think that when people talk about macros, there tends to be this sort of dichotomy between the very simple sort of push matrix style macros, which are just templating code, and these sort of CORE.ASYNC macros, which are rewriting the code, are basically a compiler in their own right. And these are ends of the spectrum, but there's a rich sort of vein of stuff in between, right? And one way to sort of get there is to leverage the existing sort of compiler implementation, because that means that not only do we not have to do as much work, but there's a lot less chance of us straying needlessly from the semantics of the language, right? Because that's what makes our macro useful, is the fact that it is intuitive to the potential users. And so there is a adoption curve that is used often in a sort of business context or more sort of enterprise conferences in this one. But the idea is that with any sort of new idea, you have this sort of peak as people get super excited about it. And this is quickly followed by this trough when people realize that it's not exactly what they were hoping for. And I think in at least the Clojure community we're about here, right? We had the sort of Paul Graham rush of Lisp euphoria. And not everything that was promised turned out exactly as we thought it would. But I think that there's a lot of stuff that remains to be sort of unearthed here. There's a lot of interesting things to be done. And some of the examples I've given may or may not end up resembling what is done, but I sort of look forward to what the future holds. And so with that, I'll leave the floor open to questions.
I guess, is it working?
Behind you.
Here you go.
So a question is about that flow macro. So you explained it's pretty hard to reason about lexical context in Clojure and macros. Do you think it's caused by the fact that Clojure has a very simplistic macro system, unlike more advanced macro systems like Racket, where this kind of stuff is built-in functionality? Like,
so I am not expert enough in Racket's mechanism. I would point out that sort of the def syntax style templates do not allow you to do code walking consistent sort of transformations, and a lot of the machinery that exists in other lists that I'm aware of is usually concerned with this. So you have the question of hygiene. How can we safely insert a bundle of code into the middle of some other template? And that is qualitatively different than what the flow macro is doing, which is doing a pervasive transform that is sort of has to be aware of the context, has to actually walk over and transform the body that's being passed in. Does that?
Yeah.
Okay.
Hi, thanks for the talk. You've been telling us how many interesting possibilities Clojure macros open up. You mentioned that sometimes macros they are not the right choice.
Mm-hmm.
I have some similar question. So what would you like to improve in Clojure's macro system if you had a chance?
Sure. Okay. So I do wish we had something more similar to the def syntax thing that Racket provides. I think that there are a number of things that are more aggressive sort of macros that I've written, which end up being really ungainly because you just have an enormous number of these sort of nested syntax quotes, which are far less readable than sort of the code as it is. And if you had sort of a better, the flaw or the sort of weakness of the syntax quote is that it's read time. So it has no sense of any of the sort of context that it's being done. If the templates were compile time, then they could use lexical scope and other sorts of things to check, and you wouldn't have to have the really aggressive sort of gensim mechanism and everything like that. And I don't think that that's a weakness with Clojure's macro system per se, so much as maybe just the tooling in the Clojure ecosystem. Like, this is something that would not have to be a core part of the language, but I do think that there is a definite need for better tools for sort of complex code generation.
Yeah, thanks.
Do you think that S expressions are the right representation for code and binding structures?
I don't have a better idea. I mean, so I avoided Lisp for a number of years because it looked weird. And
So I'm not thinking about surface syntax. I'm thinking about the underlying syntax you use to write transformations, you know, regardless of what the surface syntax is.
I don't know. I guess I haven't seen anything better, right? I mean, you know, there's always going to be some sort of AST representation. It's going to superficially sort of resemble S expressions because that's just how it's done. And I think that, you know, for instance, having a decent pattern matching mechanism in Clojure would make some of this easier. But that's not really an indictment of the S expression representation so much as, again, the tools that we have to sort of deal with it. So I don't know. I mean, I could certainly, if someone said that they had a better way, I would certainly pay attention because I think it's quite possible. I just don't know what it would be.
Any more questions? Well, thank you very much.
Thank you, everybody.